my name is Carlos Guzman, and today I will be doing a presentation on suffix tree construction using linear time Ukkonen's algorithm. Today for the overview, we're going to be going over what is a suffix tree, what is the Ukkonen's algorithm, and how is the Ukkonen's algorithm used to construct a suffix tree in linear time. So let's go over some definition of a suffix tree. A suffix tree is a data structure tree which length m is dependent on the input string s. It is rooted directed tree with exactly m leaves. These are usually numbered from 1 to m. Each internal node, except the root or leaves, will have at least 2 children, and each edge is labeled with non-empty string. Each edge label from the node will begin with a unique character. For many leaf point I, the chain of sequence of the preceding edge labels spell out S array of I all the way to M. Now we're going to go over, this is an example of a suffix tree. You're going to notice a little special character at the end. This is known as the termination character. And this helps prevent prefixes matching with suffixes. And what do I mean by that? If we look at this entire string as one single suffix of CAG, TCAGG, you would notice that CAG is a prefix within the suffix. To create any confusion in matches, we use this termination character to help us build this tree efficiently. Now, usually when people start building the tree, they build it backwards from right to left. And we look at G, so you look at index G, you can see that G with the termination character is 8, so you could follow the path, so it's just G. That's because if we look at all the indexes, 1, 2, 3, 4, 5, 6, 7, and 8. Alright, so if you look at 8, 8 is just G, so you could follow the path. 7 would just be GG, so you can see this path here is GG. The original one is just G. 6 is AGG, but you could go over here, find AGG, and you could find 6 under G. So it's just this path here, and so on and so forth. The best part of the suffix tree is that if we wanted to, like for example, find out how many suffixes start with the letter G, we just come over here, look at this G, and we know by default everything beyond this point, so 1, 2, 3 leaves, will all start with the letter G, right? Because everything above, under this, contains G as its starting character. So we could prove it. You can see 8. We look at index 8 is just G, which starts with obviously with G. We look at 7. 7 is GG, which starts with G. And we could look at index 3 right here, which is GTCAGG, which obviously starts with G. So that was a quick example of a suffix tree. So let's move on to Ukkonen's algorithm. Alright. So it starts off by, it likes to use an implicit suffix tree, which is a modification of a suffix tree. Which the 3 things that mostly modify, that's gonna modify to make a implicit suffix tree is to remove all terminal symbols. So as you can see from these 2 images, the terminal symbols get removed. They all get removed. As you can see, an implicit suffix tree. It then removes every edge with no label. When we remove this suffix right here, when we remove this termination character, there was no need for this one, so leaf 8 gets removed, and so on and so forth. Now the last rule is to remove every node that does not have at least 2 children. In this specific scenario, there is no node that doesn't have 2 children. This is kind of a common sense rule, because in reality you will never have a node that doesn't have at least 2 children, because nodes are normally created when there's 2 separate paths, right? So for example here, like this is a single leaf. A node won't get created here unless we have to do a split somewhere. So for the most part, a node will always have two children. Alright, so then we're going to talk about the algorithm keeps track of the suffix tree construction via 5 variables. The first 3 are known as active points. So the active node is the position where the current suffix is being inserted. So it's basically, it'll be the node in which we're going to insert the character from. And then we have the active edge, which is the current edge that we're working on, and then the active length, which is the remainder of the current edge. Or I like to call like this within that current, because some of the edges will have multiple characters, so it's just the length where we last left off. And then we have the remainder, which is the amount of repeated characters added implicitly. It increases for each match and repeated character, which means that every time we insert a character into any of the branches, it goes up by 1. Right? Every time we find a match for that character, we go up by 1. Alright? And it decreases after a split or an internal node added. So anytime we add a new node or a split, we subtract it by 1. So we add by 1 and then we subtract it by 1. So when the remainder value reaches 0, you'll move on to the next character, which means that anytime the remainder hits 0, we just go to the next index of the character. So if we say we're in index 1 of the string for that character is S, and the next one is T, once the insert happens and anytime the remainder goes 0, we just go on to the next one. And then we have the global n variable, which just basically keeps track of the inserting character index. So it just keeps track as at what index are we pushing characters through. But this variable is going to come very handy to help us build a tree efficiently without having to go back and adding characters to certain edges. Now let's talk about some of the logic for splitting then adding a node. So while the remainder is greater than 0, right? So that's one of the big keys, is the remainder has to be greater than 0. We split the active edge. If the active node is the root node, then we decrease the active length by 1. Right? Else, if no suffix link set the active node to the root node, else follow the suffix link to a new active node. Now, what are suffix links? These usually occur if when splitting an edge and inserting an internal node, and the inserted internal node is not the first node created in the current step. Meaning there's going to be a scenario where we are inserting a character, right? But it's not the first time. We'll have to insert it and do splits on multiple edges. This in return will create suffix links amongst those edges. It connects the previous inserted node and the new node with a suffix link. So those will create, it's just, what this enables us to do is to reset the active point. Remaining inserts stay at constant time. So it's basically, it generates a shortcut while we're inserting new characters. So it's like a new map. So the suffix link will get generated once we have to repeat certain insertions of characters or splits. So we got the algorithm components logics. The first one obviously is to build the suffix tree, which will pass it a string variable. And then for each character within that string, which is C, we call upon the extend suffix tree C and pass it the character. In this component, the extended suffix tree, the character gets passed. If the active edge does not equal none, we insert a split of active point, else insert a leaf. Then insert a split active point, create a branch, add a suffix branch. So anytime the edge is not a none, the active edge, we insert a split, otherwise we insert a leaf. Alright, Let's go over the steps for the Ukkonen's algorithm with an example. I decided to keep the original example we used earlier with the C A G T C A G G. This has the termination character, but I'm not gonna go that deep. For most of the part, we don't use it, so it's just current presentation. So, and then these are the indices for these characters. So we got 1, 2, 3, 4, 5, 6, 7, and 8. Alright, let's start with the first insertion, which is C. So, as you can see, once we insert C, we look at the active node, which is 0, or also known as the root node. The root node, right? And then we look, is there a path for C in this root node? There wasn't, so we added a new leaf, right? At that moment when we have a match, right? Remember about adding remainder plus 1? So that's when we add plus 1. We also added the n one from 0 to 1, so we added to n, which now makes it 1. But since we added a new leaf, we got to subtract the remainder by 1, which then puts it back to 0. Now that was index 1. Now we're going to go to index 2. Go to the next one. So at the next step, n goes up by 1. So this is the cool part. Since these are character representations, I'm putting up here for you to see what's actually getting added to that edge. And the algorithm will actually use this global n, which basically tells it to go from 1 to n, which automatically adds the a, right? So then, and then obviously remainder goes up by 1 because there's their match. And then we go back to the active node, which is 0. Is there a path for 8? There's not. We add a new leaf. We give it that edge, we give it a 2 to n. And then we subtract the 1, going back to 0. And as we talked about earlier, anytime the remainder goes to 0, we move on to the next character. So the next character, the next one coming up is going to be G. Alright, now we start inserting G. Remember, we're using this n, so it automatically adds the G to the previous branches, the previous edges and leaves we created. So that's the best part. We don't have to go back and add the G to them. It automatically happens because we're using this global one that went up by 1. The remainder went up by 1 because we got a match, right? Now we go back to the node, which is the active node, which is 0. We go back to it. Is there a path for G? There is not. We create a new leaf. We subtract by 1 for the remainder, making it back to 0. Anytime remainder hits 0, we move on to the next one, which is going to be a T. Once again, we move to T. We add 1 to the n, making it 4. Plus 1. New one's 4. We got a hit, so we add plus 1 to the remainder. Right? Since we're using the n again, we don't have to go in the previous edges created. We just add, it just automatically gets added to the n. We go look at what's the active node, which is 0. We go to 0. Is there a path for T? There's not. We create a new leaf. Then we subtract 1, making the remainder 0. Once it hits 0, we move on to the next one, which is Z. Now, adds a plus 1. Got a match. I mean, it moves n up to the 5 because that's 1, 2, 3, 4. So we're in the 5th index, right? So that's why this is 5. We added plus 1 to the remainder. And as you can see, since we're using the n, they all get the C at the end. Now we go back to the active node. we look up, is there a path for C already? There is. It's in this edge. That will end up making the new active edge C, right? And then the length goes up at what part? So since it's the first one, 1, the length becomes 1. So at this point is where this C is at. Since we didn't add no new leaves, the remainder remains the same and stays at 1. So then we go to the next one. We're about to go add A. We go to A. We add 1, making this the new 6. This is 1, 2, 3, 4, 5, and 6. Alright, we're using the n still, the global one, so all the a's get added to the n, as you can see. Automatically get added to the n. Now we need to find out where a goes. Previously we're at 1. You remember previously we were at 1 and 1? Well, we added 1 right now for the remainder because we're adding the a. Alright, so we were at this point right here. We were at active edge C of the length of 1, which is C. So can a go in there? It can. So it goes into the second one, so the length goes up plus 2. Because we're right here, this is the active, it's 1, right? And 1 is the next character A? Yes, it is. So therefore it goes up, the length will go up by 1. Since we didn't add no new leaves, the remainder stays 2. And now we're going to add G. Now we're adding G to the n. The n goes up by 1, making it the new one 7. We go remainder up by 1, making it 3. Now we were previously, it was 2. Previously, hold on, let me erase this real quick. Previously, it was 2. Right, so we're going to go back. So we were in the active edge. We're going to try to insert. In the active edge, we were in C. Active edge C, but this is 1. We were in spot 2. Can we insert this G and the next one? Yes, we can. In spot 3. So as you can see, CAG does exist still. So this becomes 3. So let me erase that. This becomes 3. A new edge length, the active length. Becomes 3. So right now we're in this active edge, so we're keeping track, you know. There's with the active edge of C and the length of 3 for 3. There's a new one, so we know that CAG does exist from 1 to 3. It's keeping track with the length. Alright, so let's go to the next one, which is going to be the final character, G. So let's see what happens. Now we inserted, now we did plus 1, making the n 8. But something weird happened here, right? So let me explain this. This step kind of jumped a lot of stuff out, but I will explain it in a few. As you can see though, the G's are getting added to the n of all of them. But here something happened. Before we were on edge C, 3, and remainder 3. Now we're adding, it becomes 4. So we add plus 1, making the remainder 4. Right? So we were at 3. So before we were at active edge C, and we were at 1, 2, 3, right? But now we need to add another G. When we're going to go to add another G, the fourth spot, the fourth length, was T, which couldn't work. So now we have to generate a split right here. So we ended up splitting here, we made this just 1, 2, 3 for CAG, and then we did a split, adding 2 leaves. So every time, remember, you add a leaf, you have to subtract the remainder, then it gives us 2, right? That gives us 2. And now we're gonna go to the active. So at a split, we end up moving everything over. So now, in this split, the suffix link gets created to node 0, and we move to the next one, right? So now the edge goes up by 1. Now we go to A. So we're moving to A, right? A, we gotta add the G. So the length, so now the lengths also change. So anytime we do the split and we move over, we subtract 1 from 3, giving us 2. Right, so from the active edge, we need to go to 1, 2. But then we get to the same problem, right? Now we got a match here, but we're going up by 3, so we're gonna have to do another split here. So let's go to the other split. So the split happens again. When a split occurs again, since the original suffix link was to the root, it now goes from 5 to 7. We changed the variable, the length. But when this happened, we moved, A was here, this was 2, and 2. Since we had a match, we add +1. That gave us 3. But during the split, because T didn't work, we had to create 2 more leaves, which subtract ends up giving us 1 right here for the remainder. And then we move over, we subtract the length, that ends up giving us 1, 2, and then we move over to the G. Down here, the G branch, we move the active edge over to the G. So let me clean this up a little bit. And then it's 1, so it's 1. We go over here, we need to insert the G again, which is going to push it up to 2, right? But if we look here, we look at G, the next one is T, guess what? Another split happens. So now we split again down here for branch G, right? So as soon as we hit 0, so originally it was 1, so now we have a match +1, right? We generated a split, so at first it was +1, give us 2. We generated a split, which created 2 new leaves, and we subtract by 2, which equals 0. Another suffix link was created from 7 to 9, right? This closed out this one because we started here, so we only had to go to C, A, and G because we started at the C branch, at the C edge, so we only had to go there. So we already knew from the active node, we moved over, so now it's closed, right? Is 0. Whenever you go to 0, it closes off the loop, the while loop, and we're basically done. That basically built a suffix tree for us. So now let's go over what Ukkonen's algorithm applications are. One of the most common one is for like compression, right? So finding multiple how many times a suffix appears or multiple characters and stuff like that is very important when building compression algorithms. So that's one of the key applications for this algorithm. Pattern matching or finding distinct substrings, or if there is a substring at all, it's just within the string is also could be used and make it easier to identify. So this concludes my presentation. I hope you guys enjoyed and learned something from it. And that's all I got. Thank you for your attention.